Hello, and welcome to the first of a series of screencasts on LaTeX, the scientific document typesetting system. This series will eventually form a self-contained video short course on using LaTeX. Our primary audience is students learning LaTeX for use in their coursework, but we hope these are accessible and useful for everyone. So in this screencast, we're going to learn about LaTeX and how it works, think about its advantages versus a word processor, and then give some places on the web where you can find and download LaTeX to your computer or use it in a browser. So what is LaTeX? LaTeX is a software system that produces professionally typeset documents. It was created by computer scientist Donald Knuth for typesetting technical documents with lots of mathematical notation in them. Typesetting mathematics is still its main strength, but the system is now capable of typesetting all kinds of documents, including research posters, complex graphical objects, and even sheet music. LaTeX is very different from a word processor, which is a single program on your computer where you type in text using formatting styles provided by the program itself. LaTeX instead is more like a programming language. You type in your content into a text editor and then insert commands into the text that will control the appearance of the output. These documents that contain the source code all end in the file extension .tex. Once the text document is created, you then compile the source code using the LaTeX system that is separate from the text editor used to edit your content. Once the code is compiled successfully, LaTeX produces a PDF that contains the finished product. Other file types, such as encapsulated PostScript, are also possible for LaTeX to produce. This three-step system is more complicated than using a single word processor, but in some ways it's actually simpler because the source codes are small, since they just contain text and contain no separate formatting. The source codes can be shared and used across multiple platforms with no compatibility issues, and because you can create templates for documents which you can reuse over and over again with minimal changes. And one of the big advantages of LaTeX is that it is absolutely free, and variations of it are available for Word, Mac, Linux, and many other operating systems. In the next screencast, we'll get started with making your first LaTeX document, but between now and then, you'll need to gain access to LaTeX, and there are several ways to do this. If you're a Windows user, the standard LaTeX system is called MikTeX and can be downloaded and installed from mictex.org. If you use a Mac, the standard system is called MacTeX and can be downloaded and installed from tug.org, that stands for Tech Users Group, /MacTeX. The MacTeX extras are utilities that you might find useful, such as an equation editor, but they are not necessary for installation. If you are a Linux user, your Linux distribution probably already has LaTeX installed along with the operating system. Check your package management system and see. If it's not installed already, you can install it from there. There are also some web-based versions of LaTeX that require no installation at all. The most popular one is ScriptTeX, which allows you to enter, typeset, and store a limited number of documents online. The upside of ScriptTeX is that there is no installation necessary and files are stored in the cloud. The downside is that you have to be online to use it. You don't get the flexibility of a local system, and unless you pay a subscription, there are only so many documents you can have at one time. Chances are your professor, a friend, or a Google search can be of help in installing your system if you should run into any roadblocks. So in the next screencast, we'll get started using your LaTeX system to start making a simple text and math document. See you there. Hello, and welcome to the second screencast on LaTeX. In this video, we're going to set up your very first LaTeX document, just a simple document that just works with some basic text. In the process of doing this, we're going to learn about how to find a good text editor for your LaTeXing needs, how a basic LaTeX document is structured, entering text and how LaTeX handles basic text formatting such as white spaces, how LaTeX goes about compiling and then practicing compiling LaTeX source to a PDF document, and then finally running through some basic debugging tasks in the case of errors. Now before we go on, you first need to have access to a LaTeX system. The first video in this series gave some places to go to access LaTeX. Once you have access to LaTeX, either on the web or on your own machine, you can continue. Before we make a document, we need something with which to make it. As discussed in the first video, LaTeX documents are written as plain text and are then compiled into PDFs. You need a text editor for typing out LaTeX source code. A text editor is a program that allows you to type in input from the white keyboard without any special formatting. Fortunately, most LaTeX installations come with text editors, especially designed to work with LaTeX. MikTeX, the LaTeX distribution for Windows, comes with a program called TeXworks. TeXworks is also available for Mac and for Linux. MacTeX for Macs comes with a program called TeXshop that is simple and full-featured. Other good text editors for the Mac include TextMate and TextWrangler. ScribTeX, the web-based LaTeX system, has its own editor built in. All of these programs have a feature called syntax highlighting, which means that special LaTeX commands you use are highlighted in different colors so you can tell them apart from regular text. Before moving on, find or install a text editor for your LaTeX installation and open it up. For all the screencasts you see in this series, I'll be using the editor TextMate on a Mac. Other text editors will look slightly different, but the basic operations will be more or less the same. Here we are in a blank text editor. Let's jump right in and start making a new LaTeX document. The first thing we have to do is tell LaTeX what kind of document we are starting. So in the first line, type /document class, curly brace, article, close curly brace. This is the first example of a LaTeX command. The slash mark tells LaTeX that what's about to follow is a command and not just text to typeset. The command document class article loads a preset collection of page and style formats that would be suitable for an article. There are other classes available such as exam, letter, or even poster. The curly braces indicate the input to the command document class, which we often call the argument of the command. Now that LaTeX knows what kind of document we want, we need to tell LaTeX to begin the document. So type /begin, open curly brace, document, close curly brace. Here again we see some standard syntax, a slash to indicate a command, the command itself, and then curly braces with the argument inside. Now put in a couple of spaces and type /end, curly brace, document, close curly brace. This is a special kind of command called an environment, which we'll discuss in a later video. But all LaTeX documents must include the document class command in the first line, a begin document line, and an end document line. Everything that comes before the begin document line is referred to as the preamble of the document, and later we'll be putting special document-wide commands up there. The document itself will go here in the middle. Let's make our document just a single sentence, hello world. Now save the file to a convenient directory. I'll just use my desktop. You can call the file whatever you want as long as you use the extension .tex. Now we're ready to typeset this document and create a PDF. How this works will depend on the text editor you are using. In TeXworks, there's a green Go button in the upper left corner of the screen. Make sure the adjoining pull-down menu is set to PDF LaTeX and not PDF Tech. In TeXshop on the Mac, there's a button in the upper left corner of your screen that says Typeset. In ScribTeX, there's a button that says Compile. Whatever method works for you, click the button or execute the command to typeset. If we've done everything right, there should be a moment when LaTeX compiles the document and then the output is produced. This is probably a PDF output, but it might also be called a file called a DVI file. The difference isn't important right now, as long as we have something that looks like this. If you got an error message, rewind and make sure that you typed everything in exactly as it was stated with no extra spaces or the wrong kind of parentheses, and try again. So now we've successfully typeset a document using LaTeX. Notice that if you check the directory where you saved your text source file, there are now several documents, among which are the tex file, a file with an .aux extension, a file with a .log extension, and the PDF file we're reviewing. The files other than the aux and log files are not necessary to keep around. Sometimes the .log file is useful because it contains a transcript of the system procedure that took place when the source document was compiled. Let's see what happens if I put another sentence underneath this one. I'll type, "Nice to meet you," and compile. Notice that the hard return I typed into the text editor is not produced in the PDF, but if I put two spaces in between and compile, then there's a line break. Just remember that there's no formatting in a text editor. LaTeX commands will take care of the formatting, and so what you type is not necessarily going to be what you see in the output. Finally, if you make a mistake when typing a LaTeX document, and everyone will at some point, LaTeX will do its best to tell you what the problem is. For example, suppose I accidentally used a parenthesis instead of a curly brace in the document command. First of all, note that the syntax highlighting may help. I see that the text is not the right color here, and the color could help me track down the error before it happens. But if I still don't catch it and compile anyway, LaTeX will do a pretty good job telling me what the problem is. Here, for example, it shows the place where I put the parentheses, and even though the error messages below are kind of cryptic, I can at least see the problem. Or, if I misspell the word document and try to compile, LaTeX tells me in what line the error occurred and tries to tell me what the error is. That's it for now. In the next screencast, we'll start adding mathematics into our document and seeing how text and math can live together. See you then. Hello, and welcome to the third of a series of screencasts on LaTeX, the scientific document typesetting system. In this video, we're going to expand on the simple Hello World document you made and typeset in the second video to add some mathematics. We're going to learn about how to typeset mathematics inline or alongside text, how to typeset math displayed or set off from text, how to typeset exponents and subscripts, how to use curly braces for larger arguments in exponents and subscripts, and then do a simple case study where we typeset the statement of the Pythagorean theorem. So here's the Hello World document we made in the last video. Let's add on a separate line a very simple equation, 3x plus 2 equals 7. We'll actually set this up with some text. I'd like to put the equation alongside my text here, which we call inline math. To change from text entry to inline mathematics entry, we type a $sign, then the equation we want, then close the $sign. The dollar signs mark the beginning and end of inline math entries. Now typeset it, and we see that the math comes up and it is visibly different than the text around it. Another way to enter in math is in displayed mode, in which the math will be on its own separate line and centered. Let's set up a new equation. Then we're going to type two $signs with no space in between. Then our math, then close the $signs. And for effect, let's enter in some more text underneath. When I compile, I see that the new equation has been put on its own line and centered, setting it off from the text around it. Let's suppose we wanted to add squares to all three of the variables above. To add an exponent, just use the up arrow key, which is Shift and then 6, then compile. And we see that the exponent has been added. That also works in inline mode. For a subscript, for example, if I wanted to add a sub I to the variable in the first equation, use the underscore character, then I, then compile. We can even add both superscripts and subscripts to the same variables. If I were to use a larger exponent, say to the 10th power and compile, notice that the 1 is exponentiated but not the 0. So to use exponents or subscripts that involve arguments larger than 1 digit or character, just encase the argument in curly braces as if it were a LaTeX command, and then compile. Let's end by typesetting the Pythagorean theorem, which has a nice mix of text, plain math, and exponents, and displayed math. First, I'll type out the start of the theorem. Notice that I am blending math and text together in line here. Now I'll type out the conclusion of the theorem in displayed mode, since it's important and needs to stand out. Once I'm done, I compile, and there's our Pythagorean theorem. That's it for now. In the next video, we'll look at some more mathematical commands for LaTeX, such as roots, fractions, and Greek letters. See you there. Hello, and welcome to the fourth video in a series on LaTeX, the math typesetting language. In the third video, we learned about how to include basic mathematical notation in your LaTeX document. In this video, we're going to take this a little farther by discussing more advanced math notation, such as roots and radical signs, fractions, Greek letters, the infinity symbol, trig and logarithmic functions, and then resources for finding LaTeX commands for more symbols on the web and elsewhere. Let's start here with a blank LaTeX document. It's not really blank, of course, because I put in the preamble to the document and the begin and end document environment commands. Let's begin by looking at roots. To typeset, say, the square root of 2, we'll need to be in math mode first of all, so let's type in a single $sign to start inline math mode. If we wanted this to be in displayed math mode, remember we'd use a double $sign. Now type in the command /sqrt, then open a curly brace, then the number 2, then close the curly brace. Compiling the document will result in a square root of 2. LaTeX automatically resizes the radical sign, so if I have a large argument under the root, like 1, 2, 3, 4, 5, and compile it, the radical sign will automatically fit. Generally speaking, in LaTeX, any required arguments for commands are enclosed in curly braces, like the 2 in square root of 2. Any optional arguments are enclosed in square braces. For example, if I wanted a cube root, the LaTeX command for this is I need to add one optional argument to the sqrt command between the sqrt and the curly braces. And so I'll put in a pair of square brackets, and inside the square brackets I'm going to put a 3. And when I compile this, it causes the root to become a cube root. Similarly, if I wanted, say, the 10th root, I'd put a 10 in the square brackets. For example, the 25th root of 11 will be typed like this. Another kind of common notation is fractions. Of course, you can typeset a fraction horizontally just by entering math mode and using the slash character like this. But a lot of times we want to typeset fractions vertically, and in that case we use a special command. To typeset 2 over 3 vertically, you enter math mode by typing a $sign, then type /frac, which is a command to build fractions. Then we're going to create 2 sets of curly braces with no spaces in between. That means that the frac command has 2 required arguments, and that's going to be the numerator and the denominator. So I'm going to enter in 2 into the numerator, and then 3 into the denominator, and then compile it. And just as with the square root command, if I enter in a large numerator or denominator, the fraction bar will expand to fit. For example, let's type in frac, 2 sets of curly braces, then x plus y plus z on the top, and then a plus b on the bottom, and compile it. Now with this fraction, the fraction bar is the right size, but the whole fraction itself is kind of small and hard to read. If this were in displayed math mode, then the fraction and the variables that are on the top and the bottom of it would look pretty much the same as the text that surrounds it. But suppose we don't want to go into displayed math mode, we really want this one to be in line. Well, there's a command we can add to fraction and any other thing that involves a delimiter like parentheses, as we'll see later, that will make things displayed size without putting them in displayed mode. And that is simply /display style, and then a curly brace, and then close the curly brace elsewhere to close it off. What this is going to do is take the argument that's inside the brackets, the fraction command in this case, and just simply make it the same size as it would be if it were in displayed mode, so now it's a whole lot easier to read. Now let's look at a few special symbols LaTeX can handle. Greek letters are especially easy for LaTeX. Generally speaking, these are entered in as commands whose names are the same as the letter you want. For example, if you want to enter a lowercase Greek alpha, you would typeset this by going into math mode first of all, and then typing /alpha with a lowercase a. To get an uppercase Greek letter, you just capitalize the first letter of the LaTeX command. For example, an uppercase Greek delta would be obtained by typing /DELTA. Make sure you're out of math mode, and then compile. You can also typeset the infinity symbol. That's just /INFTY. Going back to functions, you can typeset all 6 trigonometric functions just by invoking their names. For example, if I want to typeset cosine of 2 theta, I enter in math mode by typing 2 $signs, then typing /cos2, and then I'm going to enter in a Greek letter lowercase theta, so that's /lowercase t heta, and then compile it, and we get what we wanted. I can typeset a trig definition by putting together everything we know so far. Let's go into displayed mode and let's type out the definition of the tangent of an angle phi. So we're in displayed math mode, so I want the tangent, that's /tan. Then I want the Greek letter phi, which is /lowercase phi, equals, and then the tangent is just the sine divided by the cosine. So I'm going to type slash frac to start a fraction, then 2 sets of curly braces. I'm going to put the numerator, which is slash sin, and then slash phi in the numerator here in the first set of brackets, and then slash cos slash phi for cosine of phi in the denominator. And when I compile it, I see that I got what I wanted. Logarithmic functions work similarly. There's a command for the natural log, ln, just slash ln, and a command for a general logarithm, which is slash log. If you need to specify a base, we can just subscript the log like we learned in video 3. For example, the log base 2 of x is in math mode slash log underscore 2 space x, and then close the math mode symbols, and we get what we needed. So at this point you get the idea that LaTeX is very comprehensive in its treatment of mathematical symbols. Rather than showing a bunch more examples, let's just think about some places we can go to learn more. The document at this URL is a massive document of all the symbols that LaTeX can handle. It's worth keeping a copy around for reference and searching. However, you should know that some of the symbols shown in this document require special packages, which we will discuss later in another screencast, and they may not work on your system without a special installation. The website Detectify allows you to draw the symbol you want inside a box, and the website will then attempt to decipher your handwriting and then find the symbol you wanted. Note that this only works for single symbols. If you need to find the LaTeX code for something that has multiple parts, like arc cosine or something like that, then this won't do that. There's also an iPhone app for Detectify if you need something on the go, as well as an app that just serves as a LaTeX reference. Finally, this website called Web Equation works similarly to Detectify, except it handles entire LaTeX expressions. So that should be enough to get you working on a more advanced document with prettier mathematics in it. The next video will be a couple of case studies where we'll use what we've learned so far to typeset some more complicated documents. See you there. Hello there, and welcome to video 5 in the Introduction to LaTeX series. In this video, we're going to look at 2 front-to-back examples where we typeset the quadratic formula and the definition of the derivative from calculus, and this should put together everything that we've learned so far. So let's start with the quadratic formula, and the way I'm going to do this is write out the quadratic formula first, and then we'll go into LaTeX to typeset it. So we know the quadratic formula says if ax squared plus bx plus c equals 0, then, and the quadratic formula's result is pretty important, so I'm going to use displayed mode to set this off and write, or eventually typeset x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So there's the quadratic formula, and just looking at the formula and thinking ahead as to what I'm going to have to do in LaTeX, I see a couple of places where there are some exponents to take care of. This is going to be in inline math mode. All this stuff is going to be in displayed math mode. There's a root with a bunch of things under it, a fraction with some pretty large numerator. And then finally there's the plus minus sign, which we haven't learned, so I'm going to have to go look that up. So let's go over into ScribTech and start typing up the LaTeX for this. So now here we are in ScribTech with an outline of a document already set up. One new thing you see here in the third line is a comment. You can always add comments into your LaTeX code, just like you might do if you were writing a computer program. The percent symbol at the beginning of a line indicates that everything on that line is going to be a comment. It'll appear in the raw source code for your LaTeX file, but will not appear in the output. So if you need to leave yourself a note or somebody else a note explaining what is happening in a certain place, that's how to do it. So let's try to do what we can with the tools we have to set up what we hand wrote a minute ago. So first line is going to say if, that's easy enough, and then we're going to put the quadratic equation in inline math mode, so $1, and then it was ax squared, and so to get the exponent I type a caret symbol, that's shift 6, and then a 2, and just for clarity I'll put a space there, plus bx plus c equals 0. I'll close out math mode with another $, comma, then. And now here's where I switch into displayed math mode. I'm going to put 2 spaces here. The extra space doesn't really matter. All you need is really 1 space. But this helps the source code to be a little more readable. Then I'll begin displayed math mode with a double $sign. And then I'll need x equals. Everything to the right of the equal sign is a fraction, so I'm going to start with /frac. 2 sets of curly braces, one for the numerator, the other for the denominator, and let's go ahead and close off the math mode here. Now let's just fill in the blanks. In the numerator, I'm going to have negative b. And here's where we come to something we haven't learned yet. We are needing the plus and minus symbol, and we haven't seen that. So what I've got over here on an extra tab is that comprehensive LaTeX symbol guide that we mentioned in the last video. And I've gone to the page here where it starts on mathematical symbols, and I can just start doing a search here until I see what I need, and I see there it is, /PM gives me the plus minus symbol. This very frequently has to happen. I could have also gone over to Detectify and tried writing that in, but very often you're going to need a symbol that you haven't ever seen before. No problems, just go to the document or Detectify or web equation and look it up. So let's go back and put in /PM. Now what happens next is a square root, so I'm going to type /sqrt and then another set of curly braces for the argument of the square root. So now inside the square root symbol, let's put what we need. That would be b squared, again with the caret key there to get the 2 as an exponent, minus 4ac. And we're all done. So now I'm going to go with the denominator and just type 2a. That's all I needed to typeset, so I'm just going to click compile. And over in my other tab, I see that I do have what I needed. Let's zoom in so we can get a really good look at it. So that's nice looking math. Now let's try another famous equation for mathematics, and that's the definition of the derivative in calculus, at least as it appears in some textbooks. So the way you might see this written out in a textbook is to say let f, that's a variable f now, be a function. Let f be a function. Then, and here I'm going to put the definition, which again, it's important, so that's what displayed math mode is for. F prime of x equals limit as delta x approaches 0 of a fraction again, f of x plus delta x minus f of x over delta x. And in this one, we have a little bit of trailing text that would have to go back in line, and that is to say that's the derivative if the limit exists. So this equation is very similar in how it will be LaTeXed up to the quadratic formula with a few twists. I need to get this delta into the game here in 3 different places. There's an arrow that I need to find, and also I need to think about a mathematical limit command here. If I just type LIM, I don't know if that's going to look quite right. So let's go over to our editor and start LaTeXing it up. So over here in the editor, I have put in another comment to indicate to myself in the source code that I'm starting a new section. And let's just type what we can. Let f, in math mode, of course, because f is a variable, be a function. Then I'm going to go into displayed math mode this time, so $signs, f. The prime we're just going to use an apostrophe straight off the keyboard of x equals, and now I need the limit. If I just type LIM, it's not going to look quite right. It will look like a variable L next to a variable I next to a variable M. I want the LIM to look almost like it is just regular text. So this is actually a command I'm going to use. I don't know necessarily what that command is, so I'm going to go back to my comprehensive symbol list. I have no idea where it is, so I can just do a quick search for LIM. And it brings me a lot of things, many of which are substrings of something else I don't want, like delimiters. So let me advance this to the next place where I see this showing up, somewhere around in here. And I'm going to look for LIM. This can be a fairly time. Oh, I think I found it. There it is, /LIM under log-like symbols. So /LIM, fairly logical. So I'm going to go and put /LIM. Now to get the delta x approaches 0 underneath, I'm just going to subscript. And many commands like limits or sigma notation that you use for summing, in displayed mode, subscripts actually go directly underneath the symbol, not just like as an index subscript. And that's going to be the case for limit too. So I'm going to put just a regular subscript underscore here. Now what I'm subscripting here is not just one variable, but actually several things. I need a delta, I need an x, I need a right pointing arrow, and I need a 0. So in order to get all of that stuff to be subscripted, I need a set of curly braces. So everything that I put inside the curly braces at this point is going to go underneath the LIM. Now what is going to go in here is a capital delta, not a lowercase delta, but a capital delta x, and I need a right pointing arrow. And I could go back to my comprehensive symbol list and do that, or I could go over to Detectify, because this is just a single symbol, and so Detectify ought to work pretty well. Let me just see if I can draw a right pointing arrow, and it will think for a minute and eventually come back with hopefully something that's close to the right thing. In fact, there's several things that could be interpreted as this. Just a straight right arrow I think will be fine for what we need. So let's go back to here, and I'll put right arrow. I'll also say just the command /to2 will also work here. And I put 0. And now the hard part is basically over. I need a fraction, numerator, denominator, and the top of the fraction is f of x plus capital delta x minus f of x. And then in the denominator, it's just a capital delta x. Close off the displayed mode. And then the trailing text here said if the limit exists. So that ought to do it. Let's go over and compile it. And indeed, we have our limit definition right here. And once again, just notice if I could zoom in on the limit definition, looking underneath the limit, notice that the limit actually appears as regular text, which is how it's supposed to, and everything that we put inside the curly braces is subscripted underneath that limit as it should be. Hello there, and welcome to video 6 in the series on Introduction to LaTeX. In this video, we're going to step back from mathematics and look at how to format text. Specifically, we're going to see how to make text boldface, italicized, put into small caps, underlined, in a special style called typewriter style, and we're going to learn how to handle quotation marks, both single and double quotes. Here's an empty LaTeX document template with some text already in it. Notice that everything we do in this screencast will be done in text mode, and there is nothing done in math mode. In the first sentence, let's make the words bold text actually bold. So we're going to put the cursor in front of where we want to start and type /TEXTBF, that stands for text boldface, then open a curly brace, and then close a curly brace where we want the boldface to stop. In other words, we're using the command textbf and then giving the text we want to change as an argument to that command, encased in curly braces as usual. And this is very similar to how the remaining text formatting commands will work. Let's compile this to make sure it did what we wanted, and we see that the text is now bold. To italicize text, there are actually two commands. One is /textit for text italics. I type that and close the text I want in curly braces and compile. The other command is /emph for emphasized. And again, I type that and close the text that I want to change in curly braces and compile. As you can see, there's very little difference between the two. To put text in small caps, we type /textsc and enclose the text in curly braces. To underline, I'm going to use the command /underline and then enclose the text I want to change in curly braces. And there's a special style called typewriter that's good for making text look like computer commands or file names. The command is /texttt, and that's how that looks. Finally, this is not a text formatting issue as such, but using quotation marks in LaTeX can be a little tricky. For using single quotes, we can't just use the single quote key or apostrophe key that's next to the return both times, or else it looks like this. Instead, to open a single quotation, I use the quote mark that's in the top left of the keyboard. To close the quote, use the apostrophe. Likewise, to use double quotation marks, I need to open them by using the quote key in the top left of the keyboard twice, and then close them by using the usual double quote key. So that's your quick tour through text formatting. Thanks for watching. Hello there, and welcome to video 7 in the Introduction to LaTeX series. This video is about the very important subject of environments in LaTeX. In this video, we're going to learn about environments in general and how their syntax works, and then we're going to see some environments that change the formatting of text, such as centering, flush left and flush right, and environments that change the size of text. So an environment is a block of a LaTeX document that's being instructed to behave in some kind of way that is fundamentally different from the rest of the document. For example, if I had a block of text that I wanted centered, I would need to have an environment for that. It will turn out that if we want to have a column of equations that are all aligned by their equal sign, we'll need an environment for that. And so environments show up very often in LaTeX, and they all have the same basic syntax. We have to have a way of telling LaTeX when the environment is beginning and when it is ending. And we do that by typing /begin, and then in curly braces give the name of the environment, and then enter in the stuff that we want in the environment, and then tell it to end by typing /end, and then curly braces, and then the name of the environment, and then close the curly braces off. And so when you think about that, you've actually become very familiar with one basic kind of environment. And that environment is the document environment. We know all LaTeX documents, after the preamble is done, start with begin document and end with end document. So document is one kind of environment. There are others. Let's take a look at a few, and then the next few videos are going to focus in on even more. The center environment places text centered on the page. For example, if I wanted this sentence here to be centered, I would just put /begin curly brace center close curly brace where I wanted the centering to start, and then end center where I want it to end. Another environment, flush right, is like center, but it puts text all the way over to the right side of the page. Here it is in action. There's a similar environment called flush left. Environments are also how we get text to appear larger and smaller in the output of a LaTeX document. For example, to make this sentence one notch larger than regular text, I use the environment large that has a small l, lowercase l. This environment name, like most other things in LaTeX, is case sensitive. If I use a capital L, I get text that is even larger than lowercase l large is. Likewise, to make text smaller, I use the small environment. So in general, to use an environment in LaTeX, we find out which environment we need and what its name is, and then we put /begin name of environment where we want it to start, and /end name of environment where we want it to stop. There are many other environments in LaTeX which you can find out about through a Google search. The next few videos are going to focus on some of the more important of these, which are used for things such as producing auto-numbered equations, aligned formulas, bulleted lists, and tables. Thanks for watching. Hello, and welcome to the 8th video in a series on LaTeX, the mathematical typesetting system. In the previous video, we learned about the concept of an environment, which is a way of setting off chunks of a LaTeX document to behave according to some specific rules. The next 3 videos are going to look at specific environments that do some common and useful things. In this video in particular, we're going to learn about an environment for typesetting displayed equations. So first we're going to recap what we already know about displayed equations using the double dollar sign notation and introduce an alternative way to do this. Then we're going to show how to use both the equation environment and the equation star environment to create displayed equations in a slightly different way. So actually we already know how to create displayed equations in LaTeX, and that's using the double dollar sign notation. For example, let's typeset this equation offset using displayed mode, double dollar sign x squared plus y squared equals 1, and then close the double dollar signs and typeset, and that creates the equation in a nice displayed mode. Something I didn't mention earlier is that there's another equivalent notation for this, and that's using the following notation. We're going to type slash open square bracket, and then we'll type the same equation again, x squared plus y squared equals 1, and then slash close the square brackets. And then we compile, we see that both of these notations do exactly the same thing. They create a displayed mode equation. Some people prefer the square bracket notation over the double dollar sign notation, so we need to be equally proficient with each. Now there's an environment that does this as well, and it's called the equation environment. It's very simple to use. Let's do an example. We're just going to open the environment by typing slash begin curly brace equation and close the curly braces. And then we're just going to type in the equation we want. Let's go with x to the fourth plus y to the fourth equals 1. And then we close the environment as usual by typing slash end curly brace equation close curly brace. When we compile, we see we get a nice displayed mode equation just like the previous equations were. So you're probably asking, what's the point of having the equation environment when you already have the double dollar sign and slash square bracket notation? Well, the main reason is over here on the right edge of the page. Notice that when you use the equation environment, the equation is automatically numbered by LaTeX, and this becomes a very useful feature. For example, let's suppose this last equation with the fourth powers is one that I'm going to be referring back to several times in my document. I can use LaTeX to give that equation an alias or a label and refer back to it using the label. To see how this works, let's go up to here just after the environment is opened and type slash label and then curly braces, and then I'm going to choose a name for this. I'm just going to call it fourth power and close the curly braces. And now let's add a sentence to see how this works following the equation. So I'm going to type equation, and then I'm going to use a new command called ref, slash ref, curly braces, and then the thing I'm going to plug into the curly braces is the label that I typed above, fourth power, close curly braces. And then I'll finish off the sentence as follows. Notice in the argument of the ref command is the same label that I defined above. When I compile, LaTeX is going to automatically insert the appropriate equation number where the ref command was placed in the sentence. Now why this is good is that since equations are automatically numbered by LaTeX if you use the equation environment, if I happen to add a new equation up above this one, I don't want the equation with the fourth powers to be equation 1 anymore. That really ought to be equation 2. Let's go and do this. I'll go up above the previous equation and type in a new equation, begin equation x cubed plus y cubed equals 1, let's say, and then end the equation. Now, like I said, this equation ought to be equation 1 now, and the one with the fourth powers ought to be equation 2. When I compile, what you see is that since the equations are automatically numbered, LaTeX alters all the references to it correctly, so it is now correctly listed as equation 2. So you can see that if you happen to have a document that has several or dozens or hundreds of equations, then this auto-numbering feature becomes a real lifesaver. Now there's a variation on this environment called equation star. There are a couple of nice features of this environment that I want to show you, but in order to use them, we first need to add one line to our preamble. Let's go up here to the preamble area. That's any place following the document class line and before the begin document line. And we're going to add the line slash use package, curly brace, AMS math, close curly brace. Now what's happening in this line is that it causes LaTeX to load what's known as a package. That's a set of features that extends the usual features of LaTeX beyond what's normally loaded. We'll talk about packages in a lot more detail in a later video. For now, just type that line in verbatim in the preamble and let's go with it. So the purpose of equation star is to give you some more control over how your equations are numbered. For example, maybe you just don't want your equation to be numbered at all. And here's how that might look. We'll type /begin equation star, close the curly braces, and let's add, say, x to the fifth plus y to the fifth equals 1, and then end the equation star and compile. And as advertised, what you see is that the new equation is not numbered at all, and sometimes that's what you want. Or with equation star, you can also specify your own label. Let's suppose I want to label this fifth power equation with EQ5, for example. So to get that numbering, I would add the following /tag, curly brace EQ5, right after the environment is open like so. And when you compile, notice over here in the right, the new tag is generated. If I happen to add a sentence with a label, like so, following the equation, once I compile, notice that the reference is done displaying the tag that I specified. So that's a brief look at the equation and equation star environments and maybe why you might want to use those instead of the normal double $ notation for displayed mode equations. Thanks for watching. Hello and welcome to the 9th video in the series on LaTeX, the mathematical typesetting system. We're going to continue looking at LaTeX environments with the powerful align environment. So we're going to see how to use the align and its relative, the align star environments, to typeset a system of equations, a stack of calculations, and an array of stacked calculations. In the last video, we used the equation environment to typeset automatically numbered displayed equations. This is great, but you were probably wondering, what if I had more than one equation to typeset and they all go together? Here's an example of a very common instance of this. Well, the equation environment isn't built to handle multiple equations all bundled together like this. It only does one equation at a time. Going over to LaTeX, one possible solution is to stack the equations on top of each other using the /square bracket notation for displayed mode equations. But as you can see, once it's compiled, while the equations are actually displayed, they're not aligned properly. We want the equal signs to line up, and they don't. So this is where the align environment comes in. This is a powerful LaTeX environment, and that it can be used for all sorts of tasks. We're just going to scratch the surface here in this video with 3 common tasks, starting with this 3x3 system of equations. Before we begin, align is another environment that needs the AMS math package that we met in the equation screencast. So go up to the preamble and type /use package, curly braces, AMS math, close curly braces. The align environment is used to format multi-line expressions that should be aligned in a certain single place. For example, we'd like that 3x3 linear system to have one equation on each line and lined up along the equal signs. To do this, let's begin by typing /begin, open curly brace, align, close curly brace. Then we start entering the content, starting with the first line. When I get to the symbol I want to use for alignment, which in this case is the equal sign, I'm going to type the ampersand symbol and then the symbol I want to align, which in this case is the equal sign. The ampersand tells LaTeX that the symbol that follows is to be used for alignment. Now type the rest. And to end this line and start line 2, type a /. Now we'll move down and type in the second equation, using the ampersand again to flag the alignment symbol and end the line with a /. And then finally we may make it to the last line, and since this is the last line, we don't end the line with a /. Now we close the environment by typing end align. Now when we compile all this, we see that we get the equations all listed out as they should be, aligned along the symbols that I flagged with an ampersand. Notice too that the lines of the equations are automatically numbered, much like in the equation environment. This can be handy, but if you don't want the numbers, use the align star environment instead. Once you compile, you can see that the numbers are suppressed. Another place to use the align environment is to create an orderly column of calculations. For example, let's suppose we want to typeset the proof of the triangle inequality, which says that the absolute value of a sum of two real numbers is less than or equal to the sum of the absolute values individually. Here's what a shot of this proof looks like from proofwiki.org. And our goal right now is to replicate this proof. Notice that it's a column of calculations, and the symbol we use for alignment is not always the equal sign. So let's open up the align star environment because we want to suppress the numbering. Now we're going to type the first line, noting to add the ampersand equals because that's where we're going to align the rows. And then we add a double slash at the end. On the next line, notice that there is no left-hand side. In the align environment, we just simply don't put anything on the left side and just start the line with ampersand equals and then type out the rest of the line as usual. And the third line is the same thing. When we get to the fourth line, we're still not putting anything on the left side, but we are aligning using the less than or equal to symbol, which you'll remember from an earlier screencast is /LEQ. Now the fifth line. And finally the sixth line, and we are done. Let's compile it and see how we did. Finally, we can align multiple equations on the same line. Here's an example from calculus where we're doing integration by parts. Let's suppose I'm computing the integral of x cosine x dx, and I want to set u equal to x, and then put du equal dx right underneath it. And I also want to have dv equals cosine x dx, and then put v equals sine x right above it. So I want to have the u and du expressions aligned along equal signs, and the v and the dv expressions aligned along their equal signs, but I don't want to align those two columns with each other. Now the way I can do this is, first of all, begin the align environment, and then type the first line, then the second, and then end the environment. When I compile, I see the finished product is almost right, but I needed some space in between the two columns that I created. Now I can create that space by just putting two more ampersands in here, one between the x and the dv on the first row, and then between the dx and the v on the second row. This creates an aligned space that serves as a kind of separator. And finally, it looks like what I want. There's much more to say about the align environment, but these are probably the three simplest and most commonly used situations. Thanks for watching. Hello, and welcome to the 10th video in this series on LaTeX, the mathematical typesetting system. We're in the midst of looking at several LaTeX environments for doing some common tasks, and in this video we're going to take a look at lists. Specifically, we're going to take a look at the enumerate, itemize, and description environments for making lists and how they differ from each other. So all three of these environments are in text mode, not in math mode, so we won't be needing the equation or align environments here. First, let's talk about the enumerate environment. This is an environment used for making auto-numbered lists. For example, let's make a list containing the names of 4 math classes that undergraduates should take. To start, we'd open the environment by typing /begin, curly brace, enumerate, and close the curly brace. Now for each item I want to add to the list, I begin by typing /item, followed by a space, and then the thing I'm adding into the list. So let's make calculus the first entry. Now let's add linear algebra. And now add geometry. Close off the environment the usual way by typing /end curly brace enumerate close curly brace. And once you compile, you see that you have a nicely formatted ordered list. The numbering in the enumerate environment is automatic. Let's say we meant to add discrete math between calculus and linear algebra. Just go back to that place in the list and add a new item. And once the document is compiled again, notice that not only is discrete math added to the list, the other items in the list are automatically renumbered to reflect the addition. If you want to create a sublist, just start a new enumerate environment within the current one. For example, let's suppose I wanted to add Calculus 1, Calculus 2, and Calculus 3 as a sublist underneath the Calculus item. Go underneath the Calculus item and start a new enumerate environment. And then add those three items. Then close off that nested enumerate environment and compile. LaTeX formats the sublist using headings A, B, and C. You can nest enumerate and any other of these list environments up to 4 levels deep. The second kind of list is the itemize environment. Itemize does the exact same thing enumerate does, only it creates a bulleted or unordered list. If I just go and change all these enumerates to itemize, and then compile it, you can see what it does. Finally, the description environment allows you to use your own labels for list items. For example, here's a list that contains some course names in the math department at Grand Valley State University, and they'll be listed using their course numbers. So open up the environment by typing /begin curly brace description and then close curly brace. Then, for example, MTH201 is Calculus 1, so I'm going to type /item square bracket MTH201 close square bracket. The text in the square brackets will be what's displayed as the list description instead of a number or a bullet point. Then we'll just follow with the actual list entry. We'll add Math 202, which is Calculus 2, and then Math 203, which is Calculus 3. Let's stop there, and we'll close off the environment by typing /end curly brace description close curly brace. And upon compiling, you can see the results. So that's our quick tour of the enumerate, itemize, and description environments for creating lists of text. Thanks for watching.